In 2015, we found a considerable amount of very ice-rich ground in some permafrost boreholes near Lac de Gras. We believe that this is remnant ice of the Laurentide ice sheet. The presence, amount, and distribution of this ice are relevant for anticipating landscape change and for infrastructure design. Here, I will present the evidence that led us to conclude that this is basal ice and also hypothesize about its mechanism of formation. Better understanding the mechanism of formation may help us to anticipate where we are likely and where we are unlikely to find this kind of ice. My name is Stefan Gruber. Before I continue, I want to acknowledge the co-authors on the study, Pesh Subedi and Steve Kukel. The paper reporting on this has been accepted for publication and will be available soon. The DOI shown here points to a preprint where later on a link to the full paper will become available. This image shows the location in northern Canada. You can see the territorial and provincial borders, and Yellowknife has a yellow star. The small red rectangle is the study area. It includes the Acadie and Diavik diamond mines. It will be shown on the next slide. In this area, and you see the quote on the right, Dredge et al. 1999 hypothesized the existence of massive ice at depth in Hamaki Till. With the present study, we provide more and direct evidence for this. The distinction of thin and thick glacial sediments in the overview map shown here, thick glacial sediments are green, thin glacial sediments or bedrock are shown in yellow, is based on a Surficial geology map at the scale of 1 to 5 million. In this core scale, there is no Hamaki Till shown in the study area. If we were to estimate the ice content, we could underestimate it accordingly. On the lower right in panel C, you see that this simplified Surficial geology can be thought of as 3 concentric zones, and I will come back to these 3 zones later. This is the study area, and it's shown with the finer scale Surficial geology map at 1 to 125,000. And you see in dark green on the left, it shows more Hamaki Till. We focus here on the summer program accomplished with a light and helicopter portable coring rig that you see on the bottom right. The study enabling this is the Slave Province Surficial Materials and Permafrost study that was led by Barrett Elliott at the Northwest Territories Geological Survey and was heavily supported by Canor and industry. And when we analyzed the results from the drilling, we have found that topographic position, that means are we drilling a hill or in a valley, in addition to mapped Surficial geology, adds an important distinction for the type of ice we find at depth. Till and upland locations is thereby different from lower lying locations with respect to the ice contained in it. We refer to convex and well-drained locations on hills as upland till here. But let us start by looking at the low-lying locations. Organic terrain with peat accumulation up to 2-meter thickness exists in valleys and in depressions where water can accumulate. Typically contains ice wedge polygons, and in the peat we find wedge ice and pool ice, shown in panels C and in panel B. And in the mineral soil beneath the peat, we often find segregated ice that is indicative of permafrost aggradation into unfrozen material. We see this on the lower right in panel D. Here the sediment and ice are typically neatly separated in the process of segregation. And permafrost aggradation here is at least in part related to peat accumulation. We also encountered fluvially reworked material beneath the organic cover in this broad valley. It is comprised of well-graded fine sand and silt, with segregated ice clearly visible on panel B on the lower right, a little bit less clearly on the panel above because there's some organics smeared across it. Again, we see the mineral material and the ice neatly separated, and here the permafrost into unfrozen material is possibly related to sediment deposition at the surface, to peat accumulation, or both. So low-lying areas, such as this valley and the organic terrain, show evidence of reaggradation of permafrost into thawed sediments. This is consistent with an advance of tree line into the study area caused by a general warming sometime mid Holocene and accompanied by additional warming locally where trees, often along topographic lows, accumulate extra amounts of snow. This exerts an extra warming on the ground during winter and may be responsible for local thawing of the near surface permafrost. By contrast, the ice from upland tills appears visually different. This core here shown on the right has about 40 to 45% excess ice. It is comprised of wavy layers with poorly graded sediment suspended in the ice. In contrast to the segregated ice, sediment and clear ice here are not neatly separated. Intervals of almost pure ice occur, sometimes they're centimeters to tens of centimeters thick. This cryostructure is typical for basal glacier ice. But are alternative origins of this ice plausible? It's unlikely to derive from segregation because convex terrain locations don't accumulate water, and also the cryostructure of segregated ice differs from what we see here, as we know from comparison with previous slides. And also, we do have examples of permafrost in previously thawed till. This image shows a diamicton with only thin but well-defined ice lenses. This was found beneath organic terrain and likely reflects the reaggradation of permafrost into previously thawed till. Its ice content and cryostructure differ from the ice-rich material observed in upland till. This figure summarizes the upland till boreholes into a mean ice content with depth, mean excess ice content with depth. This is not a prediction of what might be found at other locations, but rather it is a visual summary of the observations we've made based on our boreholes. 20 to 80% excess ice content are common beneath the upland till. 5 of the 9 boreholes that are summarized here terminate in ice-rich material. That means we haven't seen the end of how thick a sequence of ice-rich material exists. And 4 of 9 boreholes terminate in bedrock or in a boulder. There are many intervals here without recovery that are not shown. They are also likely to be ice-rich, often where the core barrel was warmed through large clasts. We have lost the ice through melting. And then there are intervals with partial recovery but melting due to core clasts. And these are shown here, especially in the upper 4 meters with no excess ice content. So now we have a good indication that we might have relict basal ice buried beneath these upland till surfaces. Let's return to the mechanism of formation. On the left, you can see northern Canada with concentric zones of the presumed basal thermal regime of an ice sheet overlaid, as proposed by David Sugden in the late 1970s. Here, the Laurentide ice sheet is still shown as having only one dome. And I hope you can orient yourselves so you can see the Hudson Bay outlined, you see the Hudson Strait and the Amundsen Gulf indicated. The image on the right is a conceptual vertical profile through an ice sheet along a flow line. It is on the order of 1,000 kilometers long, extending from the on the left to the margin on the right. Spatially, these zones result in a concentric pattern shown on the left. The warm freezing zone that you see indicated here refers to a zone at the pressure melting point where liquid water and ice can coexist and where new ice can form by refreezing of water at vacuum from elsewhere. The mechanism of entrainment in this zone is presumed to be regelation. That means the movement of particles in ice in response to a temperature or pressure gradient. Subsequently, meltwater refreezing at the base of an ice sheet and incorporation of mineral material into the ice has prominence among the multiple processes that can explain sediment entrainment into basal ice. This is proposed by Cook and co-workers 2013, shown here as a citation, as the key mechanism responsible for producing debris-rich basal ice that can be metered to a few tens of meters thick. There are two issues worth noting here. First, and similar to the earlier model proposed by David Sugden, broad thermal zones are arranged by distance along flow lines. This is shown on the left, similar to what we've seen before, creating roughly concentric areas with dominant basal regimes on a map, and they would be concentric major domes, an ice sheet. Second, the transition between a thawed, freezing, and frozen bed is described as a patchwork. This is seen on the image on the right that only extends for about tens of kilometers, rather than a line, rise to spatially heterogeneous patterns of sediment entrainment. Let's look now at how Hook et al. 2015 described the entrainment of debris at the scale of one of those blue patches that we see here on this image. This shows a section across a local transition from melting to wet or warm, refreezing to frozen. This presumably happens over a few to several kilometers. The upper panel shows how entrainment of basal material by refreezing between the locations indicated with the Roman numerals 1 and Roman numeral 2 creates an increasingly thick basal layer of debris-rich ice. The differing shades from yellow to orange here indicate the presumed concentration of particles derived from a particular location, such as an ore body. As we are here only interested in the presence of dirty ice or debris-rich ice, we can just imagine this as being all one color of yellow. The lower panel shows this material after it has been laid down as meltout till, indicating that the equivalent of 1 to 10 meters of unfrozen sediment can be expected to be contained in about 30 meters of dirty ice. In this lower panel, all that ice has melted. Let us now modify the sketch to account for permafrost. The original graph here is on the upper left. That's the graph as contained in the paper by Hook et al. And in the part of the graph, we can see a proposed extension that accounts for permafrost. Permafrost environments, like the Lac de Gras area, once the till thickness that derives from the meltout equals the greatest depth of seasonal thaw, it will protect the underlying dirty ice from further melting. As a consequence, the superposition of the spatially variable thickness and sediment concentration of the dirty ice layer with a spatially variable ground thermal regime can result in a mosaic pattern of preserved basal ice from the Laurentide ice sheet. So we have two patterns superimposed. The one is how much of the dirty ice is produced and how much sediment is contained in it. And the other pattern is what are the thermal conditions that may later on melt out and obliterate this ice. So locally, this may explain why we find hills with very ice-rich ground, together with valleys or depressions without this ice type, and also close to surfaces with thin overburden only. This hypothesis has a number of implications. The dirty ice would be at or near its location of formation, and this is in contrast to buried ice near the margins of the former ice sheet that we know, for example, from northwestern Canada. The solute content, the isotopic composition, and morphology of the ice will differ from ice by metamorphism in the interior of the ice sheet. And with the interior, I mean spatially in the interior at the surface of the ice sheet. At the continental scale, going back to these patterns we've seen in the initial sketch of the location of the project area and in a map of David Sugden, the potential area of occurrence of this type of preserved ice is slightly limited by the conditions at the base of the ice sheet. They are responsible for the formation of dirty basal ice, and by the Holocene ground thermal regime, responsible for the melt and destruction of this layer of dirty basal ice. In summary, and to remind you, you can find the details at the digital object identifier shown here. The paper has been accepted, and the final one will be coming soon and linked here. The final paper has the images shown here. Excess ice contents of 20 to 80% were found in multiple holes in the Lac du Gras area. The thick ice-rich ground beneath Upland Hill is likely preserved basal ice from the Laurentide ice sheet, and the mosaic pattern of its spatial distribution is hypothesized to derive from the interaction of two phenomena: the spatially variable sediment entrainment, as described by Hook et al. In 2013, and the selective preservation of ice and permafrost depending on the lateral variation of the ground thermal regime and the thickness of the overlying meltdown till. The ideas presented here have happened in discussion with many people. These include Barrett Elliott, John Cummings, Stephen Wolf, Bernard Halley, Urs Fischer, and many people have been involved in the fieldwork. I want to extend my gratitude to everyone named and not named, and also acknowledge all the generous support we've received for this. If you have any questions, I look forward to hearing from you. My email is visible in the beginning of this presentation. Thank you.